So these are the points which we are going to discuss in complete demonstration. So we'll be covering entire VLSI design first, right? And then you can understand what all streams we have, why we need all these streams, and what all the essential skill set is required for each stream, and then you can decide on, right, which way you want to go. So first, introduction to VLSI institution, right? So it started in 2012, and until now we have almost trained like 1200 students till date in across these streams. Okay, so VLSI Guru institution started in 2012. Until now, from the institution, we have trained like almost 1200 students across all the streams. So this is one of the premier dedicated institution for only for technical educations. It's not like B.Tech, M.Tech course and all. It's mainly concentrate on the technical education. And intention was when it was started, like to fill the gap between your education versus the industry requirement, right? So audio problem. Just a minute. So the main point here with the VLSI institution is it's a student-friendly and transparent environment. You will see in my other slides, right, where we have captured the unique points for the institution, right, when it was started and it will not continue, right. So we are giving like 24/7 VPN facility, so you can connect anytime you want to, right. Suppose anytime if you have a free time you want to work on a project, right, you can right away start and work on. The VPN facility will be there, and you can any tool of your stream to work on and complete your assignments and labs. And targeted audience, like we see, right? So B.Tech, M.Tech, ME graduates. Those are in like 3rd year and 4th year student from B.Tech will be very helpful for their campus interviews. So you can show as a like you have some extra skill, right? So what company need? You think from the industry side, right? They need that you have to be from day one should be, they can utilize you, right, in any of the projects. If you showcase them that you already know something on the PD or any other skill set, right, so that they can right away you can be utilized there, right, and accordingly your career path will be developed there, right. The same thing for M.Tech 2nd year, because M.Tech is on only 2-year course, right. So if they have done this course in 2nd year, it will be very helpful for their campus interview. At the same time, like if someone is like seeking their career in that technical trainer, right, they also can understand, right, these things, and they can further start their career in any of the college. And the last point here is those are experienced people, right. They want to pursue in physical design, they also can understand this, right, and then change the job internally, right. If you change the job from other company, right, it will be treated as a zero experience. But if you change internally, the same experience will follow, and accordingly your designation and things will improve in that, right. So first thing we'll discuss like physical design post detail. So total we have like 12-week training for the PD, mainly targeting netlist to GDS2. Why netlist? Come again? So this will be target from netlist to GDS2. So before netlist, someone has to write RTL, synthesize that, convert to gate level, and provide the netlist. And from that netlist, you will take it to the design last stage, which is GDS2 format, right? Which is acceptable format for the manufacturing company. So that has to be in that format. for the machine to manufacture this, right? And in this complete 12 week, you will be having theoretical session and hands-on projects, right? So we are targeting minimum 2 projects here, and based on the caliber of individuals, right? So all these hands-on projects are industry standard projects, and which will be like giving an in-depth knowledge of the physical design. So we'll cover all the aspect of physical design with these projects, right? So these are the main topics of the PD course, which we'll be covering in our 12-week course. The frequently asked questions, right? The duration, like I said, 12 week. 12-week duration is only for physical design. The remaining, you can see the 12 week and 16 week. The remaining 4 week will be for Unix, Linux, TICL, and your VLSI technology basics. Right? If someone is knowing it before, will be very good. Then he can cover the course in 12 week. If someone is not familiar of this, feel very weak, is not the comfortable enough to say that I'm expert of some domain, right? Domain expertise. So we can arrange a 4-week additional course on that. So the basic intention here is like the day person is completing the course, right? He should be capable enough of all the PD related stuff, right, to be handled during their project. If you showcase yourself that you have done 2 projects, so expectation will be like 2 projects along with all the activity in the project, right? You must have encountered and completed. So you cannot say to your employer that, oh no, I don't know TICL, right? I have not done TICL, right? That's a basic understanding, right? Because all the programming, all the automations is being coded in TICL language. All the tools are comfortable in TICL environment. Their code is written in a way that it will be TICL friendly, right? So if you want to code anything which is like you want to automate any of the activity from your PD project, then can be coded in TICL. So that's the intention. That and apart from this, the digital designs and this VLSI technologies, if you are not understanding the CMOS and all this VLSI process, right? CMOS manufacturing process. So most of the things are related right here in PD. So once you see PD, right, we'll be covering in my couple of other slides. PD means you should know end to end, right? Many process and steps depends on the technology. So technology drives your PD job basically, if you see that way. Because at the end, your chip has to be get manufactured, right? And timing like 6 to 8 hour classroom, so 3 hour, both the weekdays, weekends, Saturday and Sundays. So Saturday 3 hour course in class and Sunday 3 hour course. So it can extend slightly, depends on the course material and topic, right? And mainly we are keeping timing in morning because some people join from the US and other geographical locations, right? That's the main reason to keep the timing 8:30 to 12:30. So it should not be too late for other people, right? And like I said, right, 24/7 VPN access. So the day, just right after demo session, once you complete a registration formality, you will be given a instruction as well as the login and ID for VPN. And at the same time, we'll provide you a sheet how to open a tool. And from day one, you are capable enough to start any of the tool and use it, right? As per the given instruction. So like I said, the minimum 2 projects will be done here, which are all 28 nanometer. I'll explain in the couple of next slide why 28 nanometer is so famous, right? There is a reason behind it. And the targeted projects what we are keeping here is 300K gates and more. Why I put more here is depends on, like, say, my intention is here to divide all people in three groups, right? And each group will be executing the standalone project. And all these standalone projects we can club and make a big hierarchical chip, right, at bigger levels, so that we can get exposure on block level implementation as well as top level implementation, right? So both sides we can learn. And placement support, so those will be successfully scoring 80% and above in their evaluation. It's not just completion, it is scoring, right, the marks. If you score more than 80%, you will be offered job directly. That's why we're planning to tie up with some companies. And around 48 assignments will be there, in including your PD, TICL, Linux, and VLSI technology basics. So altogether it will be around 45 assignments. So on all 45 assignments, you have to score 80% and above, which will be easy as long as you follow the course, right? A very good question, right? Why fee is so less, right? Correct? Compared to any other institution, if you see, right, fee is very less, right? So he has a basic calculation, right? License really costs 7 lakh per, right? So if you see number of students, 100 if you train a year, right, from this institution, right? So directly if you see as 7,000 per student, right, the cost drastically reduced because shared between students, right? So if you see, right, other institutions, so there is a different reason to say higher fees, right? But as per VLSI Guru institution, right, we have an equation to compute the, and each factor is derived properly as per the market rate, right? So it's not just they can put any arbitrary number here, right? He put 7 lakh because this year he has paid 7 lakh. That's why we divide this, and so you will see as the tool cost changes, as the other variable changes, the cost accordingly will be changed, right? And it's like post course completion support as well as during the course also. The WhatsApp group will be created, but as WhatsApp group you cannot discuss much, right? Right? Very limited questions can be discussed, right, on WhatsApp group, because we cannot like draw some waveform or something in WhatsApp group, right? And don't try to send messages on WhatsApp group. Another the unique thing here, right? So on the same fee, right, what you are paying now, you can repeat your course. Yeah, so like I said, right, so the unique feature here is that you can repeat your course within a year. If you feel that this 3 months, whatever course you have completed, you are not learned enough, right? Okay. If you feel that way, you can repeat the course within a year, but that's limited to classroom. You cannot say, okay, I want to attend a session from some XYZ location. That's not allowed. So classroom, you can repeat that course within a year. Right? So same course will be repeated completely. It's not just some lecture or something, right? And the next FAQ, why only on weekends, right? So during weekends, you will be learning complete theory part, right? As well as some instruction for the lab, and some of the projects will execute during the weekends. But remaining time, right, will be giving you assignments and lab sessions, which you have to complete during your weekdays. That's the intention, to keep this only for weekends. The same thing. So weekends you will be learning almost like 25%. This is a technical course, right? So more practice give you more knowledge, right? So that's the intention. So that's why we just say roughly number 25%, right? So almost 1/4 you will understand during the weekends, Saturday, Sunday, which will be in classroom, and the remaining you will be doing more and more assignments and lab sessions to learn more. Yes, very good question, right? What if you miss the session, right? So we are recording almost all these sessions, but due to the limitation of the size, right, we cannot create like a cloud here. So we are keeping last two sessions, right? In case if you miss any, you can come here on weekdays and take the videos from any of the admin, right? And then you can watch them, note down, create a notes. For any doubts, can be discussed in next class. Okay. So videos are recorded. They mentioned two, right? But it may be slightly more. So based on space available, right? We are keeping. We are minimum keeping two, and we keep on deleting the older one. If you are doing project here, yes, you can show as the experience, right? There's another question comes, right? Can I show my whatever projects you are doing here, right? You can definitely show them as experience. Because at the end you are doing the project yourself, right? With your effort, knowledge, right? So you can show them as an experience in your resume. And this 4 points is like is expected that you must know before starting the PD course. The first one is digital design basics, which is anyway covered in all the BTech course for Triple E, as well as even electrical engineering also have this, right? Digital design basics. You should be able to understand what AND gate, NAND gate, NOR gate, all these basic gates and all the digital equations, right? You should be able to understand them. VLSI technology basics, if you know, very good. If not, some part will cover in course, or some part will be in the additional 4-week. Tickle scripting is one of the like must for this physical design course, because day to day you will be using tickle scripting in your physical design job. So it's like manual versus automation. So you can reduce your like almost 4 or 5 days of work to like a day, right? Or even half a day or 1 hour, depends on your automation, right? So that's create the need of tickle scripting. At the same time, Unix, right? So tool always start in the Unix environment. So if you understand the basic of Unix, so data handling and data managing, right? For that reason, you need to understand the Unix environment as well. Right? So for every bits and pieces, you cannot ask your mentor in your company that, oh, I don't know Unix, can you please help me to start this tool? Right? Initially, yes, you can ask, but over the period, you should learn that, right? Course registration. So first session for all the course, not just for PD, for all the course, first session always be demonstration. So it will give you a feel of what it is, right? This is the unique session which we are covering for entire VLSI designs. We are not covering only physical design, we are covering entire physical, this VLSI designs. And we show you how the VLSI designs are segregated into each domains. And each domain's expertise, requirement, and essential key sets, everything we'll discuss it down the slides. So first session always be demonstration, and right after this you have to make the payment and register yourself to start the course if you like. So here we have trainers, mostly from the industrial background, and almost all have like 12-year plus experience. And currently people are working in 7 nanometer. Right? So that's a very important question. So people are confused to choose front end or back end. Right? So first question always comes, I have completed Triple E. Where should I go, front end or back end? Both are essential component of any chip designing. Both are essential components, right? But there is a unique difference between both the components. So based on your capability or understanding or interest, you can choose them, right? So if you see front end requires understanding design specification, So most of the time you'll be working on the textual side, right? So you will learn all the design specification implementing in Verilog. Yeah, specifically mentioned here Verilog or VSDL, any of the language. You can implement your design and develop the test bench for the verification of the design to check the behavior of this line. On the other side, backend, you need to understand more on the tool and technology concepts. Suppose if you are working on some new technology, so you have to understand that technology, excel that, understand all the basic difference of the technology, and accordingly you have to tune your physical design flow. So once technology changes, everything changes there. We'll discuss in detail for this front-end and back-end difference to make sure you'll understand and choose accordingly. So at the end, you should not see, okay, I selected because I feel it, but I'm not interested in this course, right? So once you feel that you're interested and you are capable enough of handling all this course contents, right, then you can select accordingly. So this is the initial difference between front-end and back-end. So what creates the difference from the other institution, right? So it's more process oriented, and whatever tools we have is all industry standard tools. So we have Synopsys ICC2, which is the latest, and I think version of 2015, which is pretty latest. Another factor is the very important one is affordable piece, right? Now we'll start the technical. Any question on this course contents, institution side, or any of the basic?
Yeah, I have a question. You compare this programming languages, technical versus Python versus Perl.
Correct.
Python is further more elegant and more packages everything available. But almost all the tools are physical and they are theoretical based. So what is the reason or history behind
Why it is tickle based?
yeah, why
That's a very good question, right? Tool environment, see, Perl has lot of assumptions in it. Assumptions means predefined thing. If you are not defining ABC or something, right, it will assume, okay, by default it will assume some values or assign something. Tickle is very straightforward language. If you are not defining, it will say error, right away. Perl sometimes it will not even show error. If you are not closing any file in Perl, it will not give any error, right? But in tickle case, yes, it will give error.
my question is more like, see, there are certain things like if you get physical or your PD, you get some report preparation, all this stuff, right? Once you have it, you do PT and then you have certain number of violations and then you have to, say you have to do STA and then see the timing, right? To get those reports, tickle is not very easy.
Correct.
So if you have to do
So you have to understand difference between text parsing language.
yeah.
TCL is tool command language, right? TCL. So that language is developed for that tool command. Perl is parsing, right? So you see the how the language got developed, right? So something is developed dedicatedly for the tool versus something is dedicated developed for the parsing something, right? Text parsing. So there's two different things. Got that right? Anything else?
Hi, Srinivas.
Just
Hello.
write down your question. Okay, so the top Left side picture you can see here, right? The first one. So from where we start, the vacuum tubes, right, was the first use for the amplification. And then you can see how the transistor got evolved, and you can see the latest chips, right? SoC system on chip. So complete entire system is on chip right now. This is how the transistor get evolved, right? At the bottom picture, if you see how the area is shrink, right? You can notice here, right, the shrink factor, right? The shrink factor sometimes depends on the design as well. All design cannot shrink with the same factor. Okay? So there are always be two variety of design. One is cell dominating and net dominating, right? So what we are talking here is mainly for the cell dominating design. We will discuss in RPD course in details what the cell dominating and net dominating designs are, right? So you can see it's pretty much like you have SRAM, you have some logic and IO, right? So pretty much like a processor kind of design. So which is shrinking from the technology, one technology to another technology, right? 45 nanometer to 32. If you do the same design, you will see the shrink factor of 0.62x. So that much less area it will consume. And same thing, move on, right? So you can see there is a jump here, right? 22 nanometer and below. This jump is caused by 3D gate, the FinFET. So 22 nanometer, first time the company introduced the 3D gate transistor, right? This is FinFET. So which is causing that much further shrink. So shrink factor is not even 50% here, right? These two numbers, if you can see. The reason for the leakage. You cannot shrink up below some level, right? You will start seeing all the this power issues, right? But here the leakage is not the factor, because from your 32 nanometer, 22 nanometer, right? Lot of things have changed. Because of FinFET, you will see very less leakage. So leakage is not at all the concern. You can further reduce the gate length, right, of the CMOS. On my bottom right hand side, right, you can see the small scale integration, right? You can see this scale here. So we stop counting after ultra large scale integration, right? Because we cannot give further numbers, right? Because if you see, right, when we were using from 1 to 10, right, that was called small scale integration. Then they call medium scale, large scale, very large scale, ultra large scale. Then done, right? So you can see 10 billion, right, nowadays in the latest. So this is a Moore's law, which says like from 18 months to 24 months, right? The transistor, right, has to be double every 18 to 24 months, right, in the same area. So within the same area, if you are accommodating like 10, then next 18 months should be double 20, and I keep on going on. You can see, right? So you can see, right, this is a processor number 4004, where you have number of transistor is 2300 in the year of 1971. So accordingly, you can see the Pentium, they start almost, if you can see correctly, right, 95 and so, right. So here 3.1 million. So the same trend is still followed, right, after this 3D gate transistor. And here is this graph. Just notice this graph, right? So my right hand side, it's saying per dollar transistor, right? So in $1, let's first explain this one. So in 2002 times, you have 2.6 million gates designed at 180 nanometer technology. So this column says technology, right? And you can see how this progressively increased, right? So you can see my 20 million transistors are accommodated in my, this is my technology. If I see, this is my 28 nanometer and this is my 22 nanometer. So at 22 nanometer in the year of 2014, I can accommodate 20 million gates, right? And if you see at the same time, my cost here, right, will be 20 million transistors per dollar. So if you follow this graph, right, for this 180 nanometer, I have to pay $1 for 2.5 million gates, correct? And you can see I'm paying $1 continuously up to 20 million gates up to 28 nanometer technology. So that's why industry is still using 28 nanometer technology, because if you change the technology here, right, you're not seeing a cost effectiveness. Notice this graph, you're not seeing cost effectiveness, right, even after changing, because your investment cost, right, to build a new equipment, for new technology with the new challenges, right, and at the same time the area, right, area is also playing a major role. You're not able to shrink too much, right, comparatively. So you can see you are still paying $1 for 20 million gates. That's why industry is more inclined to 28 nanometer technology, which is more cost effective. Alright. Remember this very first integrated circuit built by Jack Kilby on 20th September 1958. And you remember when he filed the patent for this? Almost 1 year later, 59. Right. So you can say earlier days design, right, but not that complex. People used to talk of SSI, small scale integration. So if you integrate 1 to 10 transistor, they'll be very happy. Oh, you have done this, you achieved this, right? Now we are talking on 10 billion and all, right? So you can see the nowadays, right, how the things are more complex. So this is the main reason why we need each domain expert, right? We need each domain expert. Earlier days, right, one person can handle entire thing end to end, right? Because just 10 transistor or 20 transistor, right, they can visually verify. Now for 10 billion at the same complexity, if you see, right, to validate that design, to verify that design, to check the functionality of the design itself is taking more time. You need more resource also, right? So you need each domain expert to check each and every step, right? That's the main reason why we need domain expert, and that's how the domains are evolved, right, over the period. So here we start the understanding in VLSI designs. So VLSI design is mainly divided into two major categories, right? One is embedded system development and second is SoC chip implementation. Both are interrelated, right? One is ecosystem built around the chip. One is chip is built for the ecosystem. Got it? If you are not having any latest processor with the higher computation capability released, right, you cannot build the ecosystem even with that, right? Because over the period, if you see, the complexity has gone up, right? Everything is interconnected. Now it's a cloud concept, right? Everything is interconnected. And you can see the massive amount of computation is required, right? To compute that massive amount of computation, you need a powerful processor, right? So industry has to design powerful processor, and then accordingly system has to build around that, right? to make this. So these are the two major domains which are there in the VLSI designs, right? So those are having interest in like building some system and all, they can choose embedded system. And those have interest in like you to work on the technology, VLSI chips and all, right? They can choose the VLSI chip implementation. So we'll be covering more here, SoC chip implementation. So this is the basic VLSI design flow, right? So either it's an idea or any requirement, right? Market survey or something, right? So there always be two business model. One is company build a design, show to customer and sell it. The second is customer approach to the company, I need this. So in the second case, the cost of R&D will be bear by the customer because he approached, right, to build a chip. In the first case, company will bear the cost of R&D, build the chip, build the ecosystem around it and show this to customer and say this my product is better than what is available in market. So in either side, you will have the idea or with the market survey, you know that what things to be built, right? And then you divide these things into a specification. You collect the specification out of it. Suppose you want to develop a new processor. The very first thing is technology. On what technology you want to build the processor, right? What should be my clock frequency? What should be my cache memory, right? How much is my computation power? Either it's a RISC, CISC or maybe something ASIC, right? So all these specification has to be collected. So once you have a specification ready, you will be building a architecture. Architecture will decide that whether if you implement this processor design in RISC, will give you me so many benefits. If you build in CISC, these are the benefits, or something intermediate, right? So you have to fix the architecture. What architecture you want to go for it, right? And then the second thing comes, the next step is RTL coding. So RTL coding is divided into two phases mainly. One is you freshly code and second is integration, where you integrate the existing code. Suppose someone has already done the USB coding, right? Coding for the USB IP. You need not to recode again, right? You can just use it. Right? So that's how you completely build the RTL coding and then RTL verification. So whatever code you have built here has to be verified first. So there are many different methods to verify this. We'll discuss in brief in my couple of other slides. And then the next comes, right, synthesis and physical design implementation. So this is the domain which we'll explain in more details, where you build the system and send the to foundry. Foundry only accept in GDS2 format. Only accept only in GDS2 format. That will be sent to foundry and then you have your chip ready. So if we see embedded system here, right, the moment you have idea for new chip, right, someone has to parallelly start building the ecosystem for the embedded system, because the day chip is out, right, your motherboard and other system should be ready to test that chip, right? So these two start parallelly. Any question on this? So here we are covering the in detail for the front end. So we'll first cover front end, what all things are there in front end. Then we'll cover what all things are there in back end, and then we'll do the comparison and what is expected in the industry from the front end engineer, what all skill set is required for front end engineer, and area of interest, and accordingly we'll see for the back end. So in front end, if you see, right, the requirement gathering is like a idea or market survey, or you get some customer is approaching and asking for some new designs. So once you have the information ready that what need to be designed, then you collect the specification of that, build the architecture around it, same thing, and then you model that architecture first. So the language uses System C. So if someone is very good in System C programming, he can right away choose that, okay, I'll go with the system modeling. So each are the domains. So someone will be expert in the market survey and collecting the information that what all new chip is required in market in next 2 years, right? So that's how the forecast, right? Sometimes you must have that some project is getting cancelled at the last minute in the PD execution time frame. So someone has collect the specification, build the architecture, verify that, generate the netlist by RTL integration and coding, and it approach to physical design. They're working from first 1 week and the project cancelled. Okay? Sometimes happens, right? The main reason for cancelling because it's not worth to make chip of that. Maybe market is already having the same chip, you cannot sell that, right? Or maybe some different reason. So if you see engineer salary is fixed, tool cost is already paid, except the engineering hour, company is not losing anything. If you think that they have built the entire chip and that chip is not able to sell in market, you can see how much they will lose. The foundry cost is much more than engineer cost, right? Okay. So that's how this. So everything ends at the cost at last, right? If your chip cost is too high, you cannot sell in market, then there is no use of that, right? That's the another requirement why we need domain experts, right? So that we can cut down on number of engineers, make the automation and meet the time to market. If two companies are working in parallel, right, on the same product line, so which one release first will get the market, right? Capture the market. Correct. So there are a lot of factors which drive the domain experts, right, in the industry. So if you see, the design modeling is being done in System C coding. Right? If someone feels that he is very good in System C coding, they can right away choose that domain, right? And after this, you will have RTL coding and integration. So coding is like freshly done, right? If some piece of code need to freshly done, that engineers will be put on and then they will be. So integration is very easy in a sense that it's already reused, right, in the previous projects, and again you are reusing the same verified code, right? So you need not to put more effort to retest this code, right, or revalidate this code. This is already pre-validated, right? So you can save time here, right? And once you integrate the entire RTL, the tool called Spyglass, which will do the sanity check. So once you integrate everything, all the signaling is properly connected or not, that will be done in Spyglass. So here we are giving a brief idea of the domain as well as the tool set required of the domain. After this, you will be having functional verification. So you have to check your build RTL whether I'm expecting XYZ functions, or am I meeting the same or not. So that functionally you have to verify. You can see the tool uses QuestaSim, VCS and NCSIM. So not all three tools are required. Either one of them can be used, right? So you can see in each step, right from here you can see each step you need some tool, correct? because of the complexity, right? The single person, right? You cannot handle more than 5 or 10 gates easily can be handled, but once we are talking on the RTL size of like billion gates or something, right? It is difficult. That's you need the tool, which will save time as well as you will meet the quality. The next step is formal verification. The same thing, formal verification is Jasper and INCC formal. So any one of the tool can be used to verify the formally your RTL. After this, you'll have GLS. GLS is gate level simulation. So once your RTL is formally verified, you'll see, let me give some expected input waveforms. I'll give some waveform, right? My inputs A, B, C, D, and E, F is switching at so and so time. I'll check the response. So at the end, whatever architecture you have, right? You have some set of inputs, set of outputs, right? Any system you think, right? Even your mobile phone or something, right? Mobile phone is having human interface, right? Or it's like with a tower, it's continuously having interface. The moment it receive call, it will automatically send some set of inputs to the processor. The processor will pass and search that call number into your contact list and show you the name or this person is calling. So some amount of processing is being done, right? So in the gate level simulation, they will give some waveforms at the input and validate the response at the output. So intention here is to give you a brief on the front end. What all steps are there and what all tools are used in each of the front end. Though you may be interested in PD, but you can see what all things are there in front end. So for GLS also we have used all the same 3 tools: cluster sim, VCS, NC sim. And after this you have power aware simulation. So in earlier technology, people will not think much on power, right? But now, as you shrink much, right? So you can think on the same reduced area, you are pushing more logic, right? More logic means power. You can see the power factor has gone up, right? Every time you shrink the technology, power factor gone up by the same number, right? So power requirement. So you can see for the small area, you need more power. So there should be some verification to be done on the chip, right? That the some area should not be very much problematic at the end in the chip, right? Suppose if you manufacture your complete chip, right? The moment you plug it, turn on, boom, right? Because we have not properly evaluated these conditions, right? There could be a peak power requirement where all the power hungry circuits are sitting next to each other, right? And they are checking more power from the architecture. So that has to be verified in the early stage, in the front end itself. So design is not yet implemented, right? It is still in the logical form, right? In the textual form, right? It's not implemented. So right away you can validate. So you can notice here, right? We have same tool set, but with the different additional input, right? Input is UPF, Unified Power Factor. So it gives the information on domain, what all domains are there, and working on what all voltages, right? It gives the complete domain information, right? Now at the other side, backend. So these are the unique domains in backend. So synthesis is one domain, DFT is another domain, then physical design, custom layout, SPEF extraction. These are the unique domains, right? So the expectation will be one person will be handling minimum 1 or more, or means maximum 2. So if you see synthesis, right, the synthesis job, it will be receiving a RTL and converting to gate level netlist. So this is the very first step which will convert from the RTL to gate level netlist, right? So in RTL coding, you will write A dot B, ending, right? Here it will convert to actual gates. So input A, input B will be ending, and Z will be provided and going to next stage. So here you will see the gate level netlist, and the tool used is design compiler from Synopsys and RTL compiler from the Cadence. So either one of the tool you can use it. Right? The other step in backend is DFT, design for test, right? Actually speaking, this is an overhead for the design, because in true test case, this logic will never ever be used. This is used only for testing. So if you think of 10 billion gate design, minimum 10 to 20% logic will be DFT. This will make sure your chip is testable. Suppose you manufacture 10 billion gate design and you are not able to boot up that device. It's completely dead. So DFT will help you to see the root cause of the problem. It will give you the exact root cause of the problem. It will nail down with the help of this testable logic. You can understand where my problem is, so that in next design I can fix it. Correct? Otherwise you cannot extract anything from the dead chip, right? So that is a very basic need on this. Sometimes if your chip is not boot from the proper regular sequence, right, then you can use DFT serial. You can boot that device from the DFT logic side also. So overall, if you understand DFT, so they will generate some test pattern, right, to catch the faults. They have a variety of faults identified, right, stuck at 0, stuck at 1. So during manufacturing, if some bit is being short to power, right, then it will be stuck at 1. If it's short to ground, it's stuck at 0, right? This can be happens, right, during manufacturing, right? So that is the need for the DFT in the design. Though it's overhead, right, but you need it, because you cannot be, you invest so many $1 billion, and at the end you can say I cannot test even this, right? It's a dead chip. Okay. So it's a cost overhead, but for the testing of the device. So these are the tools, present DFT Max, and even RTL compiler also have this capability to insert the DFT logic. So DFT is another domain, right, where you have different. So how to insert DFT, what all compression methods are used, how to expand this, and how to test it, validate. So all are a different unique domain. So DFT is another domain, right? The next is, after the DFT insertion in this netlist, you have the physical design. Physical design will be discussing more in details after this, right? So if you guys can see, the tool set is ICC2, Innovus, all of this. So these are 3 different companies which are giving the tool set. So once technology changes, right, all this tool company has to be upgrade their tool set, because if that is not complying, then no one can even do PD for this, right? So PD is totally rely on the tool. If tool is not complying to that technology, you cannot work anything on that technology. Though you are using your brain, you are using your automation skill, you are using political commands, everything, but tool, at the end it is stuck at the tool. If tool is not compliant to new technology, you cannot work on this. At the same time, custom layout. So in PD we have a lot of reuse standard cells. You need not to design AND gate every time. You design once, all variety of AND gates, and reuse n number of time for the technology. So that designing of that particular AND gate or particular memory configuration is done once in the layout. So layout is also further divided in two major categories. One is analog design, where person will be based on the specification, based on the given specification, he will be designing all the equations with all the width, length, calculation of CMOS, gain of the amplifier, noise ratio, right? All these things will be calculated on paper, and then they arrive with the dimension that I need. This is my dimension of my MOSFET. This is my connection of this entire system. So that first drive on the paper, and then they build in the layout. So driving that equation and plus the layout is my analog design entire system. Only implementing of a person is not driving all the equation, nothing, right? It just implementing is the layout work. So you can see a major difference, right, between these two. So analog designs, company mostly prefer PhD holders and masters and all, right? Because you have to drive, right, each and every equation. And to drive this equation, you need to understand in-depth knowledge of CMOS. Correct? You have to understand in-depth knowledge of CMOS and then calculate the gain and all the factors, right? So first designing and then validating your gains and everything after this in the SPICE simulation. Okay. So that's called analog design or full custom design. Okay. In the other side, layout, where you are just implementing the derived equations. Just implementing the, someone has derived that this is my W by L, these are my connectivity in so and so layer with this much width, this much spacing. All these instructions are already driven, right? You just implement them. Is my layout. So some company have a dedicated layout team where they use either diploma holders, ITI, or BTech. Either of this one. Okay. But both are called full custom design. So you can see overall in full custom design, the things are very limited, right? Because you need very high amount of manual job, right? Maybe driving the equation. If you think of like 5, 6, 7, 8 CMOS, yes, you can drive easily. If you think of like 20, 30, 40 CMOS, it's very tough, right? Once these CMOS are interacting each other, you can think of the complexity of this, right? How your analog equation will change. It's not just on and off in digital, right? Analog have sinusoidal waveform, right? Complete. Which MOS is my saturation mode, which is my not in saturation mode, right? All these modes will come, and as per the mode, their equation will change accordingly, right? So it's very complex. So for such complex things, the design size will be limited. Correct? So first limitation is design complexity. Second limitation is manual, right? It's too much manual. So either case, it limit that, because you cannot give like 1 year for designing. Okay, one person is designing USB 4.0 from past 10 years and not even done, right? You cannot, industry cannot wait that much time, right? So that's the need of PD, physical design, where they can say, okay, I can tolerate 90% of quality, but time is shrink to almost 10%. So if analog engineer is like taking a month, right? PD engineer can do it in 1 day also. Even lesser, right? Depends on the two then. Though quality wise, yes, analog will be highly accurate and all these things, right? But 90% of quality is good enough to meet that time, right? This is a simple example, but if you see in industry, there are a lot more things, right? And the second bottleneck is they cannot handle bigger design. That's the biggest bottleneck for this full custom design. So over a size, you cannot even build the system, right? Now we are talking of 10 billion gates per chip, right? So you can think that we cannot even afford this much time, right? The SPEF extraction is part of TD. SPEF extraction, you can see extraction, right? SPEF is standard parasitic extraction format, exchange format. Standard parasitic exchange format, right? So this is a unique format, right, to exchange the parasitics. So we have two components in parasitics. One is resistance, one is capacitance. So if you draw any layer in PD, right, physical design, that layer will have resistance as well as capacitance, right? So that has to be extract out and exchange in a format of SPEF. Because SPEF is my standard parasitic exchange format, right? This is my exchange format, right? So these things, so you can use for the SPEF extraction, we use QRC and StarRC. Either of the tool can be used for this. Either of the tool can be used for this, right? So these steps which are including PD, right? So physical design, some part of custom layout, SPEF extraction, STA, physical verification. These everything will be covered in the course, right? So next will be static timing analysis. You have built your system, but is it meeting that 2 point something gigahertz clock frequency or not? Or maybe some clock frequency given, right? So that has to be validated here. So that validation will be done with the help of prime time SI. SI means in signal integrity, right? And another tool is Tempus. So these are two tools from two different companies. So either one can be used. Both are this sign-off tool. The very last and very important step is physical verification. So is my design manufacturable? Am I meeting all the required rules, design rules to manufacture? All these things will be checked in the physical verification. So we have two tools, one is Caliber, another is PVS, physical verification system. Same way, these are from two different companies. So you can see pretty much right, in back end, the jobs are completely dependent on the tool. If tool is not compliant for the particular technology, the job cannot be done. So once you have done your physical verification, your chip is manufacturable, right? Then you do the post silicon validation, right? Which will be, so this have two steps. One is before sending the data to manufacturing company and after receiving the manufactured chip. So both time you will test it, right? And this is also a tool dependence where the tester is being used. We'll take a small break. Okay, that is good. Okay. I need a charger. Okay. So like I said in VLSI front end, you need to learn protocol. You need to implement protocol given a choice, right? If they allow you to RTL design, and then remaining is the verification. We have to run different test bench with the different conditions to be run on the RTL code to validate that particular protocol. All right. So here, if you see the majorly you need a this many skill set. So where you have to understand specification, architecture, memory mapping, and registers, right? For this particular protocol. So once you change the protocol, definitely this thing will change. Correct? And it's keep on changing. It depends on the your project and protocol, right? And the next skill set requirement is you just need not to know the language. You should be able to code also, right? So coding done by one person and coding done by second person, if you synthesize that, there may be a lot of difference, right? That's why you have to understand the different set of rules, right? So there are a lot of books on this, right? Code with so and so method to get So if you code in a method A, you will get this much size of RTL gates. If you code in method 2, right, you'll get different size of this, right? There are some known conditions because over the period BSDL start long back, right? So people have identified if you code in this format, you will see this problem at the end. So that's why they create the do and don't list, right? So don't code this method like that. So all these things also you have to learn along with the language. You may be very good at language, but to code anything in that language, you should understand what should not be done. And that's applicable in any learning system, right? What can be done any way you can, right? What cannot be done, you should understand that. Okay. And you need to understand all these verification language as well. And at the same time, front end flow design and verification both is technology independent. This protocol remain the same, right? Even if you implement in 28 nanometer, 45 nanometer, 32 nanometer, 22 nanometer, any technology you implement, it does not change, right? And at the same time, as you are not working in too much of graphics or manual, right? It's only on the text side. So changing one to another tool will be easier, will not degrade too much in the QR quality, right? Quality of the design. So user need to know commands for compilation, elaboration, optimization, coverage, simulation, logging, waveform dumping, all step with the various options. Right? So even if you change one tool to another tool, it will not change because your coding, right? Your coding style is fixed, right? Which will determine the complete quality. Correct? Your coding style will determine the quality. Even though if you change the tool for the verification or intermediate, it will not make any difference. If you change your coding style, then whatever tool you use, you will get the bad result. Right? At the end. Got it? So that is the unique difference why it is technology independent and you can easily change the tool. So tool A to tool B you can easily change. And like I said, the majority of job opportunities are in the verification domain. The same reason, right? So those people have developed the protocol, they are keeping the designing part there themselves and then sending the verification for. Now at the other side, backend. So the very first thing, right, you have to understand and excel, not just understand the tool. Whatever tool you want to use or you want to go with that, right, you have to understand the, it's not that you understand tool, you have to understand the how tool understand the design. Got it? How tool understand the design. And how tool understand if I'm giving ABC some input, right? That you have to understand so that you can manipulate later on, right, as per your requirement. So for backend, that's why the very first question of interview is which tool set you have worked on your project, right? And that is the only reason why we pull up this synopsis, ICC2. ICC2 is the latest one for synopsis, right? And second thing, learning the new technology, which is very important, right? If you compare the earlier technology versus the today's one, right, the latest one, you will see a lot of changes in that, right? Earlier days, people hardly care for power and all, but now its power is the major driving factor, right? Even it can reset your entire design. It can make you reset your entire design, yeah, if this factor is not met. So you can see so many driving factors are very like important in the latest technology. So you can see how things is changing with the new technology. So you have to first understand the technology, right? What is this technology? What all basic things are there? What is the difference from the previous technology to this technology, right? All this minute difference you have to understand. And as well, you have to understand how the chip is getting manufactured. So once you change the technology, it's like a from the company side. So from the manufacturing company, once they say we move to some new technology, it means they have changed their entire machinery. So you have to understand what all exact step they have changed. Correct? Because that exact step is the key which will differentiate from your one technology to another technology. What was the key problem in the earlier technology which drive the movement for new technology, right? Over the period, companies are evolving, right, their machinery and making sure you will have less chance of and less error, right, less problems, right? That's why you can see 20 nanometer is almost like 99.9% yield, right? That's how the yield improve, right? If you see latest technology, it's very low. So that's how slowly it will progressively becoming better and better. So you have to understand and excel the new technology, understand the difference, why you need the new technology and what all things are changed, and how this change is affecting my physical design implementation. Correct? The understanding is not enough, right? You have to convert that understanding to your flow, to your physical implementation execution flow, right? At the same time, you have to understand the basic flow of PD and how you can best utilize this flow to meet your power, performance and area. All these parameters you have to meet, right? So you can see changing the tool is very difficult as your PPA is very well tool dependent. Sometimes it so happens that person has manufactured one chip in tool A and suddenly engineer B comes and then he did the same step, same PD execution in different tool and shows that, hey, I can achieve better area, better performance, more clocking frequency, right? And less power consumption. So you can see it's pretty much tool dependence. Pretty much tool dependent, right? Your execution. So majorly, if you divide any PD work, right, in three major steps. So first step, first always, so once you decided your tool, once you decided your architecture, technology, everything is decided now. Now you are starting your real execution. Then the three steps will be, first you are validating the flow. You tune your flow as per the changes, right? Suppose your flow was built for old project, now you are starting new project with some new technology, change, tune that. Tune all the minute details required in that, right? And first design always be targeting to meet the architecture. Suppose if you are building some new architecture, right? Your main focus will be on architecture validation, right? That this architecture should be able to manufacturable, right? And give my all proper whatever architecture level things are there, right? In the second design, once I'm redoing the same design, that time I'll think for power, performance, area. First, I will not think that, right? First is architecture, right? For any new architecture, right? We have to think that way first. Like I said, it's you need to be like a tool expert, the very first and most requirement, right? So at the same time, how you make yourself tool expert across all the tool. So first understand entire basics of this. Then understand from the tool how tool understand the design. Then only you can understand different tools, right? So far I have worked almost on 4 to 5 PD tools, and I understand all the tools, right? It's damn easy. Once you understand one tool carefully with, with the all sorts of way how tool behave, right, under different conditions. At the same thing, you can see in the other. Basic skeleton remain the same. Basic skeleton across all the tool remain the same. Should not too much afraid of if tool change. So company always seeing, did you know the basics or not? Did you know the all the minute details of the technology, how things are changing with the technology? Because tool commands, if they give 100 tool commands and say, okay, learn them in 7 days, you can learn easily, right? Easy, right? Because flow is anyway set, right, by the company. You just need to tune somewhere here and there, right, as per your requirement, right? So you have to be tool expert and should be very good in TCL, tool command language scripting. It will save lot of time. If you see in your any of the job requirement, right? If any of job requirement, if you see for PD, they specifically write scripting TCL. It save lot of time. It save lot of time for yourself, right? If you have some last minute changes to be done, right, before your project completion, if you start doing manually, it will be very tough. It's consume time, right? If one or two change, yes, you can do. If like 1,000, 2,000 and more, right? You need automation for this. Right? In automation, sometimes you need multiple stage of automation. You write something in Perl, parse some information from some file, right? Use that file as an input in TCL with the tool internal commands. With the tool internal commands, you can generate your expected algorithm to target some problem. So that's how you tackle the issues, right? That's why we say you have to learn Unix also. Some of the Unix commands, right? A single commands will give you, like if you are coding in TCL, it will be like 20 lines, but in Unix, single line. The simple best example is counting the lines, right? Counting the line in a file, WC-L and then file name, done, one shot done. If you write in TCL, you have to first check file is exist or not. Open the file, read all the lines, counter and all, right? But anyway, your code size is bigger, right? This is a simple example. So same way you can see other also, right? And the next is you have to be good in VLSI technology concepts, right? Which anyway most of the MTech students know, right? But understand from the manufacturing side. You have to understand, you always try to understand from the how this chip is getting manufactured under the step A, step B, step C, and so on, right? How machine is processing that particular step to meet this requirement. That you have to understand. It's not just you know the flow, right? Okay, yeah, I know the flow. Because that will determine lot of things in your physical design implementation. The very simple example is chemical mechanical policy, right? So name says chemical, they use chemical. Mechanical is like a roller, right? Kind of something, and it's just a rubbing. So this is a small chemical and rubbing the surface. So if you have two steps, one metal is very high, one metal is very low. You can see how much pressure will be there on this, right? While rubbing that, because everything should be smooth at the end. So because of the stress, sometimes this metal will get pulled off. This is a very basic mistake, right? But if you understand the chemical mechanical policing, right, step, you can think, okay, that much gap is not required, and you can manage accordingly in your PD, right? So VLSI technology understanding is must for this. And the next is should be able to accommodate changes in the project cycle, as the final date is fixed for the project, right? Any mistake is done in entire world, right from the beginning till you receive the final input, will not push the project. Depends on the mistake. If it is like completely screwed up, then done, right? If it's a small mistake, it always be asked a PD engineer to accommodate. A simple thing, can you please accommodate these many changes, right? So you should be able to accommodate the changes in that. You plan for your PD execution for like 20 days, right? But immediately you receive something in between, which cause so many problems. To target these problems, again you say your manager, I need another 5 days. You say no, accommodate. So there you need the skill set. You need the automation. You need all your knowledge, right? Everything will be utilized that way. And how VLSI backend changes with the technology? Yeah, very much. Everything, even entire things will change, right? With the technology. And like I said, right, this is the last stage of this, right? Physical design, right? All wells if end wells, right? Correct? If your execution is not correct, physical design, then whatever effort was put before, right, will not be useful. So here is the basic SoC chip implementation flow. So till now we understand difference between front end and back end, right? So as per your skill set, right, what you feel that you are capable of, you can decide which way you want to go. So first is skill set, second is your interest, right? Skill set can be developed, right, over a period, but interest cannot be. So it is always start with the idea or market survey, right? The chip requirement, and then we collect the specification. Then in the virtual environment, we validate that architecture, whether it's feasible or not. It's not just something you think arbitrarily, okay, can we make this chip? Which is not possible, right? So there always be a virtual environment where you test your. So everything is here. If you see, right, up to now is a soft. Maybe either some coding in some language, right? And you are checking in your virtual environment whether this coding is possible or not, right? And then division comes here, right? Then division comes here. So hardware. So this part is my board. PCB designing is my like embedded system kind of stuff, right? So you will say I'm going to design some this processor, right? Even I heard sometime optical processor some have designed, right? Rather than normal signaling, opticals is some optically they will communicate the signals, right? And also design something. So someone will be working on the package PCB and board side, so that they will have the chip out, right? You can directly plug into the board and test this. And in hardware, like we discussed earlier, also full custom, and semi-custom. Semi-custom is your complete design. And in semi-custom also it divides two main level of working. One is block level and full chip level implementation. Full chip level, or sometimes people call system on chip. System on chip or block level, right? So you can see here, right, in this picture, you can see small boxes, right? So some people will be working on entire chip, some people are working on because this entire chip will be around like cannot be done by single. The amount of computation requirement will be massive. Supercomputer cannot build it. So if you see entire ecosystem development cost, final product cost, your final result and final product cost with your all the spec. Spec is not just like a your frequency, right? Right? It has even cost factor also. Cost, power, everything will be there, right? So everything you have to meet. So at the other side, we will be having a full custom design, which is primarily divided in three parts, right? One is the standard cell design. So there's a set of engineers. Any new technology, they'll be working on standard cells, designing AND gate, NAND gate, NOR gate, and all the basic components required. It's not just one AND gate. They will design AND gate based on 1, 2, 3, 4, 5, whatever is required, right? Based on that. So there's a set of people. But this is mostly reuse. So design once, validate, tested once, reuse in entire cycle technology. If any problem comes, then again some changes. So this is like a piece of work is completely reused. Completely reused, right? So if you think that industry is stuck at some particular technology, not changing the technology, you can see this job profile. Correct? So this will be a problem. So once you change any technology, there will be a lot of pressure to these people to release first. Because until they are not releasing the basic component of the design, you cannot build yours. You cannot build your chip. And the second thing, like we discussed, analog. Analog also has to be developed for any new technology based on new rules and new metal specs. But over the period, just a minute. Okay, so you see, and full custom is divided in basic three different domains. Called domains because you need domains. You need a domain expertise, right? You can develop a new standard cells, right, based on the new technology. Likewise, like we said, right, analog IP. Limited with your number of components, right? Size. Right? There are a lot of limitations in there. Not many things are automated. But with the new technology, there are the driving factor. You cannot use old technology PLL, right? The clock generator part, right? You have to build PLL again, right? For the new technology. So SRAMs, DRAMs, right? This is another area where people are working. So you can see in full custom also, we use domain expert, right? Time to market requirement. So these are the different areas expertise. Okay, so regarding FPGA, okay, regarding FPGA, right, FPGA development will be here, right? So in FPGA means it's like reuse, right? So you just program your any of your architecture in any of the FPGA board and then test it, right? So development will be once and then multiple times can be reused. Right? But development has to be done here only, right? But in FPGA you will have memory component also, right? So it's not exactly just here, right? Here will be the final execution, but you need SRAM, right? You need analog components in FPGA for your generating the clocks and all, right? So it will be like an entire design only, right? Right. FPGA also someone will be working on board also, right? Board level. So it's like a different. Suppose here you have, I need to design some new FPGA for so and so configuration, right? And then you calculate the specification of that FPGA with the clock, power, area, performance, right? Everything you will capture, right? And then test that in the virtual environment. So it flow goes the same. Any design, new design you start, the flow goes the same for the chip designing. Okay. So that is the need for the domain expert, right? Because of the time to market is too small nowadays. So another factor is software. So right from the after the virtual verification done, right, we divide into hardware, software, and package. So this part you can see here, right? It's like embedded systems. This is your completely execution, backend execution, right? Backend plus front-end execution, and this is your complete software. So that's how the division happens, right? So here we'll see in next slides what is my front end and what is my back end. So some part of front end is here where you develop the specification, architecture, and all, right? And some part of front end will be this one. Right? Someone has to integrate the RTL, right? RTL coding is also my front end job, right? So let's see the detailed understanding between the full custom and semi-custom designs. So full custom is your analog design, SRAM design, or standard cell design, right? So mainly targeted for high performance, right? It is dedicated engineers with proper understanding of technology to complete the task. So these people should, because they are drawing each and every connection manually, right? So they should understand more and more on the technology side. It's not automated yet, right? And this implementation are highly designer dependent because of the analog calculation part, right? Right? These are highly designer dependent, right? Not everybody can calculate like for a bigger system or this width and length of the CMOS, right? Each and every CMOS and the gate gain and all this factor, right? It will be very complex, right? So if you put any new engineer, he will take some time to learn that level, right? Correct? To meet the time to market, you can say it's a highly engineer dependent, right? Designer dependent, basically. You cannot just replace one person to another person, right? Because the moment you replace, entire thing will go. And like I said, it's very difficult for engineering change order. You can say, okay, change this layer to so and so, place this component, this location to other location, right? But once you do that, the entire thing will change. Because you have to redo complete thing, right? It's manual effort, completely manual effort, right? You have to redo this thing. And other limitations cannot have a bigger designs. Because time to market is, to meet that time to market, that whatever timelines you have, right? It's very difficult, right? And at the same time, as you have a lot of reuse here, right? So once a team has designed standard cell, they will push them to some other analog design implementation, right? Because a standard cell is designed once and reused, right, multiple times. So you don't need too many people there, right? You'll keep bare minimum people who can just implement the changes and then shift remaining staff to other domain which are similar, which are same in the full custom design. And the very best thing of this full custom design is highly performance and well controlled in the variation. If you see in each lower technology, you have a lot of variable components, right? Because of the technology shrink, right? So every shrink in the technology is adding lot of variables in it, and each variable is impacting your design in terms of variation. If you are expecting delay of like 10 ps, with this variation your delay can even go to 15 ps, which is like 50% sometime, right? Even it can go more based on your variation. Okay. On the other hand, the semi-custom design, which is like our digital design PD, right? You will have advanced tools are used to handle the design complexity with multi-thread and multi-CPU. Sometimes both. Multi-CPU means from the same machine, if you are using multiple CPUs, it's multi-CPU. If you are using two different machine, you're using 4 CPU from machine 1, 4 CPU machine 2, it's like different thread. So that's how they understand this between thread and CPU. Multi-thread and multi-CPU both can be possible. So designed for the time to market with PPA, power performance area. So mainly target is highly complex design to meet the time to market requirement. And consume more power, because here you have highly controlled, right? So your power and everything will be neatly calculate first, right, and then implement. Here is just tool is doing, and tool has a limitations, because for entire big design you cannot go and calculate each and every MOS and all, right? So comparatively for the same design, if you implement here versus implement here, it will consume more power. And here mostly automated. Why mostly automated? Because sometimes you engineer has to do automation integral, right? And it can handle bigger design, very much comfortable for engineering change orders, right? Any changes can be made easily, right? Within a short duration of time compared to the full custom design. You need dedicated engineers for each block. So each piece of work will be done by single person. Here you may need more people for the same work. Here one person will be handling entire thing, right? Like block 1, block 2, block 3, right? So block 1 be owned by single person. That's how the division is done. A re-implementation of the same design is taking less time. Like I said, right, the first is you have to tune your flow. Second is validate your architecture. Third is your final, right? So if you are redoing same thing, your flow is already set, architecture is already valid, right? So you can save time. So re-implementation will be in lesser time. So this is one of physical design engineer tool, right? Here we can see this box. These all things are expected from a PD engineer working at system on chip level. So you can see main is like all the main steps, and if you are building RTL, RDL, distribution layer, RDL, then verification will be routability and physical verification. These things will be checked, right? After this, you'll be doing all IO planning, composite band, everything, right? And then the check will be ERC, electrical rule check, and routability at the same time. So full chip level, right? Designs are like your bump limited design or your package limited designs, right? So major two categories are there. So bump limited means you have set of number of pins is fixed. So based on number of pins, you cannot shrink area further, because for each signal pin you need IO pad, a dedicated cell, right? Because of that cell and all the geometry requirement of that cell, you cannot shrink further. Right? At the same time, the package you have selected, company has targeted some package, right? You cannot go and increase, modify the package, right? Because board is already developed for that package. Your entire ecosystem is already developed for that package. So because of this limitation, you cannot grow or shrink the area, right? Package. Then other step comes like RTL integration. So at this full chip level, mostly it is integration. Now we'll be writing the complete 10 billion gates code, right? So a small piece of code will be written and they integrate at this SoC level. So our plan here for this PD course will divide each group of 3 people, and they will be executing some project, and that project will be called as a block level implementation, and same will be used for SoC implemented system on chip, right? We'll build a entire bigger system with that happen. So you can experience both, right? So once you have done the integration of RTL, then the verification steps comes RTL verification, static timing analysis, and power. You can see here, right? The next is the power start coming here, right? So right from the RTL, you have to check the power. Then you will be adding your testable logic, right? So that your chip can be tested after manufacturing, right? And this verification is coverage. If you add some X percentage of logic, how much is coverage? Am I able to cover 100%, 99%, or 80%? Right? Generally 99.6 is the lowest number. What is highest? 100. So 99.6 and below will not be allowed. Should be above. Means entire design is testable now. Right? That is the DFT strategy size. And after inserting the test logic, you will see, is it not disturbing my timing? Right? If by mistake the testable logic is inserted in a path where you are not able to meet your clock frequency of 2 gigahertz or something, right? Then this has to be tested and corrected here itself. And then your PD work will start. So if you think of the system on chip level, it's mainly partitioning, means dividing the logic, and assembling. So first you divide and give it to the block level owner, and then assemble it later on, and then test your. So their corresponding checks will be your physical verification, which is very important check, right? This check will determine whether your chip can be manufactured or not. For the particular technology, whether this chip can be manufactured or not. It's not checking clocking and timing and all. No. It's checking can be manufactured or not. And the next is STA, which will completely validate on clocking. It doesn't care for the manufacturability. It cares only for the timing, whether it can work on this clock frequency or not. Right? The next is power. So there should not be a scenario where 2 power hungry blocks are sitting next to each other. Your distribution is uniform, right, across the chip. If you have 2 power hungry blocks which is fetching more and more current, right, and they are sitting side by side, your entire network will collapse there. Your entire network will collapse there. Your chip will not work. So all these parameters will be tested at the system on chip level. Then third is logical equivalence check. I start with this RTL. I inserted this DFT. Am I logically equivalent to this RTL or not? AND gate can be size 1, 2, 3 or something, right? But should not become NAND gate. Or should not become OR gate or so, right? The logical equation remains the same. So that check will be done here. That's called logical equivalence check, LEC. And then low power checks. So this low power check is like CLP, conformal low power checks, which will be determining the domain crossing. Suppose you have 5-6 domain in your block. Domain A is my switchable, domain B is my always on. So anything going from switchable domain to always on domain should be isolated. That is the rule. So all this type of rule will be validated here. Another rule is if you have level shifters, right? High to low, generally we don't need level shifters, but low to high you need level shifter. If signal is going from low voltage domain like 0.8 VDD to high voltage domain 1.2 VDD, you need level shifter. Correct? And high to low, you don't need level shifter. Condition 2 should not be too much different. Right? So all these checks will be done here in the conformal low power step. Now after this is my complete design as long as it meets my architecture requirement. If you have any changing ECO, engineering change order, if you are not meeting timing, then you do some changes and revalidate entire thing. Correct? If your physical verification is not met, make the changes in the design and validate again entire thing. Right? If your power is not met, make the changes in design, engineering change order and validate again. So that's how this is a loop until you converge for all these requirements. Right? So in this picture you can see, right, this is my complete PD picture, right, physical designing, right? Where you can see partition and assembling. So these small green color lines you can see, right, around this, these are my IO pads. These are my signal IO pads, right? And around this you can see these boxes. These are my macros. And this boundary you can see yellow lines, right? That's how you have divide your blocks. So at SOC level for PD engineer, job will be placing all the IOs as per the connectivity. There should not be case that this IO is talking to H block and you have placed here. Correct? So this kind of case should not be there. So carefully you have to place all the IO port pads, right? These are the pads, IO pads around this, right? And you should not give too much of like zigzag shape, right? So always prefer a square shape or rectangle. But sometimes you don't have choice, right? If this memory is like not like just a rectangle, right? Some shape, right? Different shape, some macro. Accordingly, you have to cut the block, right? Right? Or maybe some congestion is there at this edge. Again, you have to increase the area here. You cannot disturb entire chip. You can just change this edge here, right? If you're seeing congestion. So this block will become rectilinear, right? So that judgment you have to take if you're working at SOC level on this. Okay. Now coming to the block level implementation. So from this right, you can see this block is being cut, right? Small portion, and you are working on this small portion, right? So you can see a clear division here, right? FEOL, front end of line. Understand the naming convention, right? So people must have heard, right? Back end, back end, back end. What is back end, right? Here you can see the backend. This is BEOL is my backend. Back end of line. So there is a clear division of layers, right? To manufacture a single CMOS, you need lot of layers, right? And to connect between two CMOS or between two cells, right, you need metal layers. So this entire metal layer connectivity is called backend layers, right? And up to this contact 0 is called my front end layers, right? Don't get confused with the front end RTL coding and all. No, this is my front end of line. FEOL is being called, right? That's a division, right? So you can see your entire PD work is connecting the box, right? That's your job. It looks easy, but very tough. How to connect, how to place and connect, right? Your job is just to connect these layers as per the requirement. But the connection the layers based on your placement. And placement is based on your floor plan. So everything you have to plan accordingly and then connect is your PD job. So your CMOS is being designed by a standard cell team. You're not designing this, right? Right? All your bump planning is done by your SOC, system on chip level person, right? He'll be planning all this IO pad placement and everything. So you bother only for this intermediate layers connection, right? Easy? So it always starts with the RTL design. So you can see this brown box, right? This is my PD job. But how things are started, I'm just explaining this, right? So it always starts with the RTL design. Then you synthesize the RTL, becomes the netlist, gate level, and then insert the testable logic, right? For the DFT, so that your chip is testable. So each block we are implementing, and then once we assemble, we'll connect the entire DFT circuit, right? So most of the things remain same for the verification side, right? Like SOC we just discussed. So PD will discuss in detail in my next slide. So physical design implementation is called BEOL, backend of line layers, right? So all these layers will be designed, and these are the corresponding verification. They are more or less same, but complexity will change. Verifying at system on chip level versus verifying in a block, the complexity will change. So if you see the previous one, right, this is my entire chip of like 10 billion gates and so, right? But here is a small block which will like 300k, 400k, or maximum 1 million. So maximum limit is 1 million or 2 million maximum. Because the moment you grow the size of the block, your server requirement goes exponentially. If you compare 300k design versus 1.3 million gate design, you will see this 300k design will be happily working on 4 CPU with like 40 gig, that's it, right? If you are running the same 1.3 million gate on the same configuration, it will be running like for days, literally days it will be running, right? 4 CPU and 40 gig. So here you have to change the configuration. So you can see the how configuration is, server configuration is exponentially changes with the design size. And additionally it is adding to the cost at the end, right? Finally it's adding to the cost. So with these limitations and time to market, you have to divide the blocks at the SOC level and execute at the block level accordingly. Any question on this so far? Physical design core structure. This is the real entire PD flow. You'll not see this anywhere, right? This is what actually it happens, right? Executed, right? So each level, your quality of report, QR is what? Quality of report. is different for each level. For each level, quality of reports means my target is different, right? So once I code in RTL, my target is different, right? I have to see sanity check, right? Whether it's linking properly or not, all the components are assembled properly or not, right? So this checks will be different. So once this check is met, then you go to next step, which is my synthesis. Synthesis will convert this Verilog or BSDL code into your gates, which will be AND gate, NAND gate, NOR gates, or your all the basic gates, right? And once, so my quality of reports of this synthesis will be your timing, area, right? Right? Performance, complete PPA, right? Power, performance, area, all these things will be checked. And at the same time, am I having all the components? Suppose RTL code, you did something like A and star B. It means multiply, right? A multiply with B. Do you really have multiplier in your library? Someone has designed multiplier in standard cell team. If no, then this check will fail here. One component is missing. Then go back, change the. If it is just a small component missing, like some special gate, NAND gate, AND gate, right? Then you can change easily. If some big component is missing, then you have to redo your RTL coding. Instead of A multiplying with B, you have to completely redo your coding, because these special components are not available in your library. So you can see, for this you have two arrows, right? Either it's going to resynthesize or either it's going to RTL change, right? So based on criticality, it will be moving. Then it comes to your floor plan, placement, and OPT's optimization. So if you see here, right, this is my PD, physical design implementation. Start from here. But you see, right, at my first stage, if it is not meeting my QR, quality of report, which will be my visibility of floor plan placement, right? Which will be my timing after placing the cells, right? Which will be my power, right? If anything is not met, right, you will be reiterating the placement. So you can see here, this side, right? This is my RTL code, converting to gates, right? And now I'm placing these gates, NOT gate, flop, AND gate, right? D flip-flop. So all these gates I'm placing. And you can see these lines, right? Vertical and horizontal line, these are my power structure, right? You have to supply power also, right, to all the blocks. So if these are not met, all the target parameters, then I will be reiterating floor plan. Suppose if I'm seeing congestion, right? If from this block to that block, if I'm having like 100, 200 nets, right, connection, and this area is congested, then I will be changing the placement and I will be iterating within the same loop. If I'm not meeting timing, means it's a medium type violation, right? If I'm not meeting timing, then I will check with the synthesis. Are you meeting timing synthesis? If no, then redo synthesis. First meet timing there, and then I will implement my block. If some path like logic depth, right? Logic depth is from one flop to another flop, how many number of cells are there. If that depth is high, because each cell will be having some small amount of delay, right? If depth is high, means delay will be high, so you cannot meet your clock frequency. Then you will be approaching your RTL designer. Hey, can you reduce the number of depth? I'm not able to meet this clock frequency. So you can see, you can see how the first step is changing my. If it is low priority, yes, we will reiterate for congestion and small issues. If for timing, yes, definitely I'll check with synthesis, and I will request for RTL change in case if logic depth is high or some other problem, right, in the RTL. So sometimes congestion can be because of RTL coding also, right? So once this is met, right, my timing is properly met, all this clock frequency, everything is met, then I will be running my clock synthesis, right? So you can see here this red line, right? So it's supplying clock for all the components. It's applying clock for all the components and then checking the timing. So once you are meeting timing after the clock build, your next step is routing. You can see the blue color line right here. This blue color line, right? So this red color line is your clock. It's reaching to all components, and all these vertical and horizontal lines are your power structure. And you can see the blue color line right here is my routing of the signal nets. So after routing of signal net, I will be optimizing for timing, right? I will be optimizing for my timing. And once everything is done, I'll say my all this PV checks, my timing, power, performance area, right? All these are met, then I'll just directly tape out, send the design to foundry for the manufacturing. If not met, then I will be doing the changes, engineering change order, right? These changes can be your timing ECUs. These changes can be your for the power, right? These changes can be anything, maybe functional change also, right? Right? RTA person say, okay, I'm not able to meet this particular specification. For this, I'm changing these 10 gates connection I'm changing. So he will generate a piece of code and you have to implement here. Right? So this is a iterative process, right? So this is my entire PD cycle, if you see. Oh, thank you. Ah, why physical design? I think you better understand, right? So far, why physical design, right? We understand and explore each domain, right? So far. So based on your choice and understanding and your interest, you can choose that, right? But if you see overall requirements, right? Requirements are really more. Day by day, you need lot of variety of chips, right? To be manufactured, right? And each chip, if you think of like a 1 billion gates, right? Will be minimum you need 300 people, right? All the domains. And there, for each block implementation, you dedicated one PD engineer. So you can see the requirement of PD is really high in market, right? And getting a good PD engineers is really tough as of now. It's very tough. People know how to run flow and all, yes, but they don't know basic concepts of this thing, right? If you really understand this, it will be very good, right? Opportunity. So in PD, you can see the how the code and idea converted to silicon, right? That's what we saw in my last diagram also, right? The how the idea and code is converted to a chip, right? So this you can feel it and see it, right? Basically, And at the end, you can proudly say, I worked on this chip, I made this chip work, right, for so and so frequency with this power factor and all, right? And how this chip will meet the fundamental requirement of frequency. Can the chip work within the defined power limits? All this you have to meet, right, at the end. Otherwise, you cannot complete your design. And how much area this chip is going to take will decide by the PD engineer, right, based on the different parameter. So to realize this chip, right, physical design technique should be implemented for designs, right? Is this possible? So overall, if you see, right from your idea to your chip, right, how you can see the each stage how things are changing in PD, right? If you really feel it's interesting, yes, go for it. If you are feeling like you are very good in the coding with ESD and SDL codings, right, then you can select that domain. Both domain have almost equal opportunities in market. RTL verification have slightly lesser, but not that low, right? Requirement wise. If you're very concerned for the market and job opportunity, yes, both are have almost equal. But PD demand is more, slightly more, like you can say 40-60. If you need 100 engineers, 40 will be RTL verification and 60 will be PD designers. That's a general ratio for the industry, right? Yeah, how this course will help you. So we'll have some detailed assignment of 42, 45. Apart from the course, right? Whatever technical theory course will cover. Apart from this, we'll have some assignments in across all the different steps, right? Even your TICL, Unix, and VLSI manufacturing technology also will be covered, right? And it gives exposure to new graduates to all required expect bring intern as on par with a 3-year expertised engineer. So if you see overall, if you complete 2-3 projects here with all your technical understanding, you can interview a 3-year experienced person and you can see you are more or less equal to that person. You are nowhere inferior to that, right? You'll be better than this. Because 3-year experienced person, right, if you see the expectation in the industry are being covered here, all these, right? So as far as you follow the course, complete your own assignments on time, right? All assignments, understand them, right? That you can be equivalent to 3-year, right? Because 4th year onwards, many things start, right? Expectation is very high. So 3-year experience means engineer grade, basically, right? The moment you grow in your ladder, right, in your company, the expectation is keep on increasing, right? So these are the main steps which will be covered in our physical design engineer course. Like we discussed, right, introduction to ASIC flow, data preparation for the PD, what all input data required, then static timing analysis, routability analysis, liability analysis, right? And for planning, placement, clock tree synthesis, routing, and physical verification. There will be some intermediate step as well, right? Like floor planning will be having power planning and all other macro placement. A lot of things will be there in the same step. These are the bigger like bullets, right? Inside this, these are the major steps if you divide PD into, right? These are the major steps. And inside each step, you will be having a lot of small steps to be done, right? Understand? So what will course material will be provided, right? The basic physical design topics, so almost all PD topics. So not just PD, right? The before whatever their synthesis, right? Sites, all these small things will be touched up. And ST design is another domain, but we'll cover here. Static timing analysis, physical verification is also another domain, right? Which we will cover here. And this reliability and radar and power analysis is also another domain, but we will be covering as part of PD. So you can fit your career in any of this domain as well. So here we will provide you the basic physical design topics, which I just explained, and you'll be having set of assignments, and we'll provide a material, notes, and scripts once we start on the project. So we'll provide some set of scripts or commands, right? The basic command, first we'll execute a basic tool, right? And then basic tool on some small project, and then we'll jump on to our real project, and then accordingly we'll hierarchically grow the complexity. So this covered the complete PD course, such as like all the same step, floor planning, placement, CTS, routing, STA and ECO cycle, right? Even physical verification also, and reliability analysis also. So like I said, job opportunity, right? So VLSI Group tied up with some various VLSI companies, right? So company directly approach here, right? And they conduct interview and right away select the candidate. That's the one way. Second is, we'll conduct the test here, and those score like the top ranking people, right? They will be directly hired to that company. So placement support will be provided based on the performance in the course assignment. Okay. So VLSI physical design training involve more than 40 assignments covering various aspects from floor plan, placement, CTS, routing, STA, industry standard projects, right? So currently we have projects in 20 nanometer. So we'll be like having 2 projects in 20 nanometer. And as per the ability of a person, we'll see something on the system on chip level as well, right? We'll try ourselves, right? So first complete block level implementation of 2 projects, and then with the different methods, how we execute at block level, and then we integrate in the system on chip level, and then we'll see, right? So we'll have exposure on either side. Then mock interviews, interview questions and preparation. So this is like upfront. Once we are discussing theory, right? Most of the questions will get covered automatically in theory part as well, right? Job prospects in physical design. So we'll be keep on upgrading that. What is the industrial job requirements, right? As per we change our anything if required to be changed in our PD course, right? Structure, we can change that accordingly. Yeah, that's a very important question. Why choose career in physical design, right? So less number of engineers with good knowledge of microelectronics, more opportunity, physical design playing an important role in SOC flow. Yes, it's very important, right? Like I said, right? All well if end wells, right? If you execute properly, everything is good, right? These are the other course offered from the VLSI Group institution. You click here, right? You'll see. So once you click on this, right, you can see what all courses are like upcoming course, and then you have this course in VLSI front end domain. There are a lot of courses are available, right? Yeah. Backend domain, you have a lot of course in backend domain. If you want to expert yourself in DFT, right, then you can choose DFT course as well directly, right? Then custom layout trainings also there, right? So accordingly, you can see a lot of courses are there, right? Which are completely given here, right? And each course have the same transparency level, right? Means this your duration, price, everything is completely updated on this on the web page, right? So you can choose accordingly, right? These are the further contact details if anyone want to contact. And the same thing is there in the website also, right? Contact details and how to reach here, right? That's more important, right? Morning 8:30 reaching here will be tough, right? So you should know, right, from where to catch the bus, and where to get down. Yeah. So you can be here or you can be here. It's all your choice, right? Okay. Thank you, guys.